Welcome back to part 3 of this series, the grand finale. It's been an awesome journey so far, and I promise we're ending on a high note. But hey, if you missed the first 2 parts, don't worry. I've linked them right here so you can catch up anytime. Now, let's dive into the fascinating world of local optima in Hopfield Networks. Imagine climbing a hill in the middle of a mountain range. You're hiking up and you reach the top of the hill. It feels great. You've got a nice view and you're convinced this must be the peak. But here's the twist. You're not actually on the highest mountain. There's a taller one just a bit further away, but because you stopped at this hill, you never got there. This is what happens in Hopfield Networks when they get stuck in local optima. The network settles on a solution that feels good enough, but isn't the best possible outcome, the global optimum. The reason this happens is tied to how the network's neurons update themselves. Traditional Hopfield networks often limit activations to values like 1 or 1. It's like having fixed steps on your hike that don't allow you to explore those in-between paths that could lead to better solutions. Continuous Hopfield networks try to fix this by allowing smoother updates, but even then, escaping those local optima can still be tricky. So how do we fix this? Enter strategies from other optimization methods. Techniques like gradient descent or hill climbing can be adapted to help Hopfield networks move past these local optima. And then there's the hero of the story, simulated annealing. It's like introducing a little randomness to your hike, taking a step sideways or even downhill momentarily to eventually find a path to the true peak. This probabilistic approach lets the network explore the solution space more thoroughly and find the best outcome. So there you have it. Local optima might feel like the end of the road, but with the right tools, they're just a stepping stone to something better. And with that, we've reached the peak of part 3. Thank you so much for joining this series. Don't forget to like, comment, and subscribe if you enjoyed the ride. Let's continue exploring the amazing world of neural networks together. All right, let's dive into one of the most fascinating techniques in optimization, simulated annealing. Don't let the fancy name intimidate you. This is actually inspired by something as old as blacksmithing. Imagine heating metal to reshape it and then letting it cool slowly to make it stronger. That's exactly where simulated annealing gets its name, and the principles are surprisingly similar. So, what's happening here? In the real-world process of annealing, when you heat metal, its atoms move around, breaking free from their positions. This makes the metal malleable, allowing it to reshape. Slowly cooling it helps those atoms settle into a stable, lower energy arrangement, which gives the material strength. In the optimization world, simulated annealing applies the same idea to finding solutions. Start by exploring broadly, and then gradually focus in on the best possibilities. Now, let's use a more visual analogy. Picture a ball rolling on a bumpy curved surface. At first, the ball has a lot of energy. It bounces around, overcoming small hills and obstacles. This is the hot phase, where the system explores as many options as possible. As the ball slows down, it begins to settle into a valley. If we let the ball cool down slowly, it might find the deepest valley, which represents the global optimum. But if it cools too quickly, it might get stuck in a shallow valley, a local minimum. This is why the cooling schedule or temperature parameter is so critical in simulated annealing. Here's where it gets even more clever. The method allows the ball to occasionally roll uphill, accepting worse solutions temporarily. Why? Because it prevents the system from getting stuck in those pesky local minima. This is controlled by something called a probability parameter, which decides whether the system should take the risk of exploring a worse option in hopes of finding a better one later. But, and this is a big but, simulated annealing doesn't guarantee you'll find the absolute best solution. It's a bit like fishing in a giant lake. You might catch something amazing, but there's no promise you'll catch the biggest fish every time. This is why careful tuning and analysis are crucial when using simulated annealing. Let me give you a final metaphor to sum this up. Imagine you're solving a giant jigsaw puzzle. At first, you might scatter pieces everywhere, just exploring connections randomly. Over time, as the picture comes into focus, you work more methodically, snapping pieces into place with precision. That's simulated annealing in action, starting with randomness but slowly homing in on the perfect fit. And that's the beauty of simulated annealing. It's inspired by physics, shaped by nature, and powerful enough to tackle some of the toughest optimization problems. Let's keep exploring how this fits into Hopfield Networks in the next section. Stay tuned, and don't forget to subscribe if you're finding this series helpful. All right. Now that we've covered the concept of simulated annealing, let's see how it's applied to Hopfield Networks. This step-by-step process is where the magic happens, so let's break it down. Step 1. Initialization of neuron activations. Think of this like shaking up a snow globe. We begin by randomly initializing the activations of all neurons in the Hopfield network. This randomness is crucial. It ensures that we're starting with a wide variety of states to explore rather than being stuck in one predictable corner of the solution space. Step 2. Traversal of neurons. Now imagine walking through a garden and checking every single plant to see how it's doing. That's essentially what we're doing with the neurons here. We traverse them repeatedly, in no particular order, to give each one a chance to influence the network's overall state. This random traversal ensures fairness. Every neuron gets to play its part. Step 3. Energy assessment. Here's where the real evaluation happens. For every neuron, we check whether changing its activation will reduce the network's overall energy. It's like deciding whether pruning a branch in our garden will help the whole plant thrive. This energy assessment is vital because it sets the direction for the network's evolution toward more stable and optimal states. Step 4. Acceptance of changes. Finally, we implement the acceptance criteria for these activation changes. This step is what makes simulated annealing so powerful. Changes that reduce energy are always accepted, that's a no-brainer, but here's the twist. Changes that increase energy might also be accepted based on a certain probability. Why? Because it allows the network to escape from local optima and explore broader areas of the solution space. It's like sometimes letting a plant grow wild for a bit, knowing it might lead to a stronger and healthier structure in the end. And there you have it, the 4 steps of applying simulated annealing to Hopfield networks. It's a balance of exploration and refinement, chaos and control, all working together to find the best possible solution. Oh, and don't forget, just like tending to a garden or shaking up that snow globe, you might need to repeat the process a few times to get the best results. Stick around as we explore even more insights. And if you're finding this series useful, hit that subscribe button and share your thoughts in the comments. All right, folks, as promised, the moment you've all been waiting for. Yes, it's time to dive into Boltzmann Machines, a topic I know you've been eagerly anticipating. By the way, if this is your first time hearing about Boltzmann Machines, or if you want a deeper dive into their workings, I've already made another video on the topic, which you can find in the playlist right here. Be sure to check it out later. Now, let's get started. Boltzmann machines are a type of stochastic neural network that work with probabilities and energy states to model data distributions. Think of it as a decision-making system that loves playing dice, sometimes making unconventional moves to explore all possible solutions. Here's the big picture. Visible neurons are the ones you can see. They handle the input data like the ingredients in a recipe. Hidden neurons work behind the scenes like a chef, combining those ingredients in innovative ways to enhance the final result. This dual setup gives Boltzmann machines their flexibility and power. The training mechanism is where it gets exciting. It's a two-phase process. In the positive phase, the machine gets data to chew on. It fixes visible neurons to specific values. In the negative phase, it's free to explore, adjusting neurons to find equilibrium. Think of this as like teaching a kid to ride a bike. First, you guide them, positive phase, then let them wobble and stabilize on their own, negative phase. And let's talk about energy. Yes, the energy function. If you want to read the full equation, pause the video now and take your time. For everyone else, here's the simplified version. Energy in Boltzmann machines is like tracking how tired a system is. Lower energy means the system is stable, kind of like how you feel after a good meal. High energy. That's the chaos before dinner is served. The activation probability of a neuron depends on this energy balance using a neat trick called the sigmoid function, which smoothens out decision making. That's your intro to Boltzmann machines. Part dice roller, part chef, and 100% awesome. We've got plenty more to cover, so don't forget to like this video and subscribe for more amazing content. And while you're at it, check out that other video for a deeper dive. See you in the next section. All right, let's take a moment to compare the energy function in Boltzmann machines with the one we've discussed earlier for Hopfield Networks. Understanding these differences is crucial because while they share similarities, their purposes and mechanisms differ quite a bit. Let's break it down. In Hopfield Networks, the energy function acts like a roadmap. Its goal is to guide the network to a stable state, a local minimum where all neurons are happily aligned with their inputs and weights. Think of it like settling into a comfy chair. Once you're there, you don't want to move. The Hopfield energy function is deterministic, meaning that every step the network takes reduces energy and gets it closer to that stable state. There's no gambling or second guessing. It's all about finding the lowest energy configuration that fits the input pattern. Now over to Boltzmann machines. Here, the energy function is less about immediate stability and more about exploring possibilities. Instead of marching directly to the lowest energy state, Boltzmann machines factor in randomness, like a dice roll. This randomness allows the network to explore a broader range of states, including higher energy configurations. Why? Because this exploration can help the network escape local minima, those almost best solutions, and potentially find the global minimum, the ultimate solution. It's like climbing out of a small valley to see if there's a deeper one nearby. Another key difference is the role of temperature. In Hopfield Networks, the energy function doesn't involve temperature. It's a straightforward deterministic process. But in Boltzmann machines, temperature plays a critical role. High temperatures allow the network to explore more possibilities, taking bigger risks. As the temperature decreases, the network becomes more focused, settling into the best solution it has found. To summarize, Hopfield Networks. Deterministic, always decreasing energy, aimed at stable states. Think of it as a careful planner who always sticks to the safest route. Boltzmann machines. Stochastic, randomized, influenced by temperature and designed for exploration. Imagine a curious traveler willing to take detours to discover hidden gems. This difference makes Hopfield Networks ideal for tasks like associative memory, where stability is key. On the other hand, Boltzmann machines excel in probabilistic learning, exploring diverse solutions and approximating probability distributions. And that's the beauty of these energy functions. They're tailored to the specific goals of each network. If this sparked your curiosity, don't forget to like the video and subscribe for more. Let's keep diving into the fascinating world of neural networks. Let's dive into the math on this slide, but we'll approach it with a story instead of equations. Imagine you're a manager at a company, and you're deciding whether or not to assign a task to an employee. You'll evaluate a few things before making that decision, like energy difference. Think of this as how much effort it will take for the employee to complete the task. If it's a small effort and aligns with their strengths, they're more likely to do it. If it's a massive undertaking, you'll hesitate or look for other options. In this analogy, the energy difference reflects how favorable it is for a neuron to become active based on the inputs it's getting from others. Probability. Here's where things get interesting. You're not just deciding based on logic, you're also rolling the dice a little. You might give a tough task to the employee if the circumstances are right, like when you're feeling confident about their potential, which corresponds to the temperature parameter in the formula. This randomness lets the network, or you, the manager, explore possibilities that might not seem obvious at first. Stochastic updates. Now imagine you're reviewing your team's workload. Instead of assigning tasks all at once, you decide one task at a time. Sometimes you give a tough task to someone to see how they handle it. This randomness, or stochastic nature, allows you to discover talents or solutions you didn't know were there. Similarly, neurons in the Boltzmann machine get activated not deterministically, but probabilistically, enabling them to explore states beyond the obvious. Let us breaking it down. The formula uses temperature, T, to represent flexibility. Higher temperature means you're willing to take risks, assigning harder tasks, while lower temperature means you're playing it safe, assigning easier tasks, or sticking to a stable state. The energy difference evaluates how favorable it is for a neuron to turn on or off, much like assessing the suitability of a task for an employee. Finally, the whole process ensures the network learns and adapts in a dynamic, probabilistic way, which is like running experiments in decision-making to find better outcomes. In summary, the math isn't just about numbers, it's about a balancing act, exploring, adapting, and converging to solutions in a smart way. It's less of a rigid plan and more of a creative brainstorming session where even the less obvious choices get a chance to shine. If this explanation sparks curiosity, don't forget to subscribe for more analogies and breakdowns like this. All right, imagine you're trying to train for a big marathon. At first, you need to figure out your goal. Maybe it's running 10 kilometers without stopping or hitting a certain time. Then you divide your training into phases. Some days are for sprints to build speed, and others are for long, slow runs to build endurance. You keep track of how your body reacts, noting your progress and where you need improvement. Finally, after making adjustments based on your performance, you repeat the process until you're in peak condition and ready for race day. Training a Boltzmann machine works in a similar way. The goal is to teach the machine to recognize patterns in the data, and like marathon training, it's a step-by-step process of practice, observation, and adjustment until it's performing at its best. Let's break down how each step in this process contributes to building a model that's ready to tackle complex problems. Step 1. Define the training objective. Imagine you're opening a puzzle box and your goal is to recreate the picture on the cover. In the Boltzmann machine, our puzzle is the data, and the training objective is to adjust the machine's weights and biases to make its probability distribution match the true data distribution as closely as possible. This step is like setting the stage by determining the picture you're aiming for and the rules for fitting the pieces together. It ensures that the model accurately captures the patterns in the data. Step 2. Conduct training in 2 phases. The training of Boltzmann machines involves 2 distinct phases, which you can think of as practice and reflection. Positive phase. In this phase, the visible neurons, which represent your input data, are set to match a given data sample. These neurons interact with the hidden neurons, and their activations are adjusted based on the current weights. It's like practicing a skill. Visible neurons are providing a structured input to see how the system responds. Negative phase. Here, all neurons, both visible and hidden, are allowed to activate freely until they reach thermal equilibrium. This phase lets the system reflect and explore different states without any constraints. Think of it like brainstorming. You let all possibilities play out and then identify common patterns. This phase helps the system learn about the data in a more holistic way. The distinction between these phases ensures that the model doesn't just memorize the data, but understands its underlying patterns. Step 3. Collect statistics for weight updates. During both the positive and negative phases, the Boltzmann machine collects statistics on how neurons, both visible and hidden, interact with each other. This is akin to an observer noting how team members interact during practice versus brainstorming. These statistics, such as how often certain pairs of neurons are active together, form the basis for calculating the necessary updates to the model's weights. It's about recognizing patterns in behavior during structured and free-form scenarios. Step 4. Update weights and biases. Now comes the adjustment phase. Using the statistics collected, the weights, connections between neurons, and biases, individual neuron tendencies, are updated. The changes ensure that the network increasingly favors configurations that reflect the actual data distribution. For example, weights are strengthened if two neurons are often active together during the positive phase but not during the negative phase. This makes the network better at representing those relationships. Similarly, biases are adjusted to make neurons more or less likely to activate based on their behavior in the two phases. This is like tweaking a recipe after tasting. It ensures the final output is as close as possible to the desired result. Step 5. Iterate until convergence. Finally, the training process repeats these steps multiple times. Each iteration brings the model closer to its goal, a probability distribution that aligns with the data. This is like practicing a musical piece over and over until you can perform it flawlessly. The iterative nature of this process ensures the model learns all nuances in the data. This step highlights an important principle. Patience and repetition lead to mastery. The network keeps refining itself until it no longer needs further adjustments, achieving convergence. This training process is robust but requires careful tuning of parameters like the learning rate, how big the adjustments are, and stopping criteria, when to end the iterations. With this, the Boltzmann machine becomes a powerful tool for uncovering complex patterns and relationships in data. If this makes sense, let's move forward to further refine the Boltzmann machine's concepts. Let's dive into restricted Boltzmann machines, RBMs, with an analogy that makes things crystal clear. Imagine an exclusive club with two floors. The visible neurons are like the guests on the ground floor who interact with their surroundings, data, while the hidden neurons are the VIP members upstairs who analyze the guest list to decide what the club vibe should feel like. Here's the catch. No guest visible neuron talks directly to another guest, and no VIP hidden neuron talks directly to another VIP. The interaction only happens between the floors. The training process. Positive phase. Think of this as the initial meet and greet. Guests, visible neurons, mingle with the VIPs, hidden neurons, upstairs, who take notes about what's going on to adjust the ambiance. Negative phase. Now, the VIPs use their impressions to update the guest list. Reconstruction. They simulate what an ideal club atmosphere should feel like, adjusting the weights to improve the reconstruction. Weight updates. The club manager training algorithm tweaks the rules based on the difference between the real guest list and the simulated one. The aim? Perfect harmony between the floors. This exclusive club analogy showcases the core idea of RBMs, symmetrical relationships between visible and hidden layers that learn to reconstruct data effectively. Now, if you're ready for more, let's keep climbing the ladder of neural network knowledge. Let's break down the phases in training restricted Boltzmann machines, RBMs, using analogies to help make these steps more relatable. Positive phase. Think of it as preparing a pizza with your favorite toppings. You have a recipe, the input data or visible neurons, and the chef, hidden neurons, observes it to decide how to enhance the flavor. The toppings are carefully arranged based on what's provided, creating a positive impression of the perfect pizza. In this phase, visible neurons are clamped to the input data, and hidden neurons adjust to capture the patterns present in the input. The network learns to model what the ideal data representation looks like. Negative phase, after serving the pizza, the chef recreates it from memory without looking at the recipe. This recreation might differ slightly, but aims to replicate the original taste based on the chef's understanding. Here, the hidden neurons are fixed, and visible neurons are reconstructed based on the model's understanding. This helps the RBM evaluate how well it can recreate the data. Weight update. The chef compares the recreated pizza to the original. If the recreation doesn't match perfectly, the recipe is tweaked, improving the chances of getting it right the next time. The weights between visible and hidden neurons are updated based on the difference between the original and reconstructed data. This adjustment fine-tunes the network's learning process. In summary, the positive phase sets the standard, the negative phase tests the reconstruction ability, and the weight update ensures the network learns from its mistakes. This cycle is repeated until the RBM becomes a master chef, perfectly recreating the input data. As we conclude this journey through Hopfield Networks, Boltzmann Machines, and their applications, it's clear how these models bring a unique and versatile perspective to the field of neural networks. Let's tie everything together. Versatility of Hopfield Networks. These networks shine in applications where storing and retrieving patterns through stable states is crucial. Think of them as the sticky notes of your brain, efficient, reliable, and ready to handle diverse tasks. Convergence properties. With guaranteed stabilization in a finite number of steps, Hopfield networks highlight the beauty of structured learning. It's like finding the fastest way through a maze. You may take a few turns, but you're always assured of reaching the exit. Energy function. In optimization, by transforming complex optimization problems into energy functions, these networks demonstrate how to untangle intricate puzzles, showcasing their practical use in tasks like the traveling salesman problem or even network design. Boltzmann machines and data fitting. These machines demand carefully crafted data to align with the Boltzmann distribution, emphasizing the importance of high-quality inputs for robust model performance. It's akin to preparing a perfect recipe. The better the ingredients, the more delightful the outcome. Future research directions. The horizon is bright with opportunities to blend Hopfield networks and Boltzmann machines into hybrid models. Imagine creating a system that learns from the best of both worlds, like merging a classic sports car's speed with the efficiency of an electric vehicle. If you've enjoyed this series, like, share, and subscribe to the channel to keep this content coming. Let's build a community that loves exploring the world of neural networks and beyond. And if you have an exciting paper, project, or idea that deserves the spotlight, let me know. Connect with me on LinkedIn. I'd be thrilled to dive into it and bring it to life here on the channel. Here's to future explorations and collaborations. Thank you for joining me on this incredible ride.